Hello friends, today we see about the various process in thermodynamic systems. So before going to the processes, we have to know about the some points which are already studied in previous lecture, but in today's lecture we take a quick overlook on them. So what is meant by thermodynamic system or isolated system? That can exchange neither energy nor matter with the environment. Matter means mass. So, in this figure, we get the actual idea about the type of systems. So, first system is closed system. In closed system, exchange of energy but not matter with the environment means the energy created in the system it exchange the system boundary, but the matter inside the boundary will not exchange with the environment or with the surrounding. This is known as closed loop system or closed system. In open system, we see in this figure that the heat means energy created in the system and the matter or the mass inside the boundary of the system is also exchanged with the environment. So this is the open system. And the isolated system means in that system energy or mass cannot exchange with the environment, means they cannot cross the boundary of the system who energy and mass. Now moving forward, we have already seen quasi-static processes. The quasi-static processes means the processes are near to the equilibrium condition. So what is mean by equilibrium? So first I will tell you about that. It is the property of a system are uniform throughout, so long as the external conditions are unaltered. The system is said to be in thermodynamic equilibrium, or in other words, a system in thermodynamic equilibrium satisfies all the three mechanical, thermal and chemical equilibriums. That is, a system is in thermodynamic equilibrium. So what is the meaning of these three equilibriums? First is mechanical, second thermal and third chemical. So we see one by one the definition of these three type of equilibrium. So first one is mechanical equilibrium. Mechanical equilibrium exists if there are no net forces between the system and surroundings, means there is no net force between the system and surrounding, and if there are none within the system also, so the system becomes mechanical equilibrium. In thermal equilibrium, it exists if the temperature of the system is uniform throughout and equal to that of the surrounding with which it is in thermal contact. So the system becomes thermal equilibrium. In chemical equilibrium system, it exists if the composition of each compound present is constant, and if diffusion and solution do not occur, then the system becomes in chemical equilibrium. So when the system completed these all equilibrium conditions positively, so that system becomes thermodynamically equilibrium. Okay, now comes again towards our point, which is quasi-static processes. In this we take one example here. So initial state, final state and intermediate state are well defined by use of PV and T means pressure, volume and temperature diagram. So sufficiently slow processes is equal to any intermediate state can considered as at thermal equilibrium. So thermal equilibrium means that it makes sense to define a temperature, means throughout the system the temperature becomes uniform and it also equal to the surrounding temperature when it is in thermal contact. So example of quasi-static processes are isothermal, isochoric, isobaric and adiabatic. So the prefix iso is shows that the quantity after the iso word is constant throughout the system. So in isothermal, temperature is constant throughout the process. In isochoric, the volume is constant in throughout the process. In isobaric, pressure is constant throughout the process, and in adiabatic the uh, entropy is constant throughout the process. So isothermal process is also called as constant temperature process. Isochoric process is also called as constant volume process, and isobaric process is also called as constant pressure process. So we have to first understand what is work and how it occur during this process or during the system. So here is a piston cylinder example. In a figure, this shows that piston moves away from the molecules. During collision, molecule loses kinetic energy. So work does the work which is positive on piston, means this fuel supply comes into the cylinder and that cylinder moving towards right as shown in the figure. At that time the work done on the piston which is positive, and in B figure it shows that piston moves toward molecule. During collision, molecule gains kinetic energy, so does negative work on a piston. So in these two processes there is one process is expansion and another one is the compression. So in expansion process, work on piston position is work on gas is negative, and in compression work on piston is negative but on gas the work is positive. Okay, now moving forwards, work during a volume change. With the same example, the force exerted which is pa, force that system exert on a piston having some area which is denoted by a, and pressure applied on the piston. So the deflection in the position, means from the main position to the deflected position, we take as a dx. So the work done is equal to F into dx, but force which we get the value is P into area, means the force acting on that or pressure applying on that area. So which is P into A, and the deflection get the value is dx. So we get the work equation is pdv means the volume change with the deflection position. So we get the actual equation which is work done at v1 position to v2 position is pdv. So now in next slide we see work on PV diagrams. So in first graph we see the graph plotted pressure against volume and the path passing from the position 1 to position 2, and the colored area, which is equal to the work done. So at first position P1 is higher and V1 is lower, and at second position P2 is lower than the P1 and V2 is more than the V1. So the volume is increases as process passes from the point 1 to point 2. So the work and the area are positive. And in second position or in second graph, we take a overlook of that graph, that the first point is at higher volume and lower pressure, and as process follows towards the point 2, the volume is decreases at point 2 and pressure increases. So the work and area are negative, shows by the hatching line, because in this figure the volume is decreases from the initial position. So there is a negative work done on the area. Now we see in the third graph that V1 pressure is same at point 1 and 2, and process follows from 1 to 2. At that time the first volume at position 1 is lesser than the volume at the state 2. So in this condition the work is positive. In this condition work is positive. Okay, now moving forwards, one point I just forget, listen carefully, that in this condition the pressure values are same. In third condition pressure values are same, so the equation becomes P into V2 minus V1. Now moving forward, before going to the type of processes, we have to know about the first law of thermodynamics. As shown in the figure, the first law related to the conservation of the energy. So this law is the same as the law of the conservation of energy, which states that energy can neither be created nor destroyed if mass is conserved. The sum total of energy in the universe is constant. Energy can be converted from one form into another form. This is thermodynamic aspect of first law. A machine cannot create work from nothing, nor it can deliver more work than it receives. In a steam generating plant, the chemical energy of fuel is converted into heat energy in the boiler, which in turn is converted into mechanical work in the steam engine or steam turbine. If the steam turbine is coupled to an electric dynamo, the mechanical energy is converted into electrical energy. If the dynamo is supplying the electrical energy produced by it to drive an electric motor, the electrical energy is again converted into mechanical energy. Okay, so this law was established by Joule, that heat and mechanical energies are mutually convertible. Heat requires for its production a definite number of units work for each unit of heat produced. Similarly, heat produces by its disappearance a definite number of units of work for each unit of heat converted. This is known as the first law of thermodynamics. Okay, so as shown in the figure, there is a heat is positive when it enters in the system, and work is positive when it is done by the system, as shown in the figure number 1. And in second figure we see that heat is negative when it leaves the system, and work is negative when it is done on the system. Means when we get the work from the system, at that time the work is positive, and when we done the work on the system, at that time the work is negative. So the formula is delta U is equal to Q minus W. Q is heat and W is a work done. So we have the value of W, we put in this equation. So now equation becomes delta U is equal to delta Q minus PdV. So we get the final equation to solve these problems. Now moving forward, we get the knowledge about the state function already in previous lecture, but with the help of graphs which are plotted pressure against volume, we get more clear view about the state function and the path functions. So in first figure A, we assume that there is a isochoric and isobaric process. So as I already told you that isochoric process means there is a constant volume process, and in isobaric process there is a constant pressure process. So in the graph, the work done within the volume range V1 to V2, and at that time there is a pressure is constant. And if we consider that the process is isochoric, then the values are varies with respect to pressure from the ranges P1 to P2. So we can find out the work by use of formula P2 into bracket V2 minus V1. And if we consider that the process A is isobaric and process B is isochoric, at that time the work done is P1 into bracket V2 minus V1 as shown in the graph B. And in graph C we see that the process is isothermal, so we get the work done with the function in the range V1 to V2 PdV. The work done by the system depends on the initial and final states and on the path. It is not a state function. And amount of heat transfer also depend on the initial, final and intermediate states. So it is not a state function. So the state function calculated by delta U is equal to Q minus W is equal to U2 minus U1 for the internal energy. The internal energy U is a state function. The energy gain only depends on the initial and final state and not on the path, even though Q and W depends on the path, but the internal energy change in internal energy is not depend on the path. It is a state function. Now moving forward, there are four types of thermodynamic processes. As I already told you, adiabatic process, in this no heat transfer by insulation or by very fast process, so the work done is negative and you get the value U2 minus U1. In isochoric process means there is a constant volume process, so Next process is isobaric. Last one is isothermal. In this process, constant temperature process, heat may flow but very slowly, so that thermal equilibrium is not distributed. So this only for the ideal gas. So generally delta U, Q and W not zero. Any energy entering as a heat must leave as a work. So thermodynamic processes are plotted on this graph as the process shows. From A to 2 is a isochoric, means constant volume process. Then on graph the process shows from the A to 3 is a isobaric process, means there is a constant pressure process. Then from A to 4, in this process there is a temperature constant, so this process is known as isothermal process. And A to 1, this is known as adiabatic process. So we already see that the first law of thermodynamics, in this law says that the energy neither be created nor be destroyed. So the isolated system equations are put into the tabular form here. Then cyclic process equation and adiabatic process equations. So in isolated system, the internal energy of an isolated system remains constant. In cyclic process, energy exchange between heat and work. And in adiabatic process, expansion means internal energy U decreases, and during compression internal energy increases. So, more about the cyclic processes, we have to know that work equals the area enclosed by the curve, but be careful with the signs. Okay, the formulas are written at one slide. Those are important formulas. So, take a look on the slide. Delta U means change in internal energy equal to Q minus W, which is related with the first law of thermodynamics. So W, next formula is W is equal to PdV with respect to V1 to V2 work during a volume change. PV is equal to nRT, which is ideal gas law. So you have to know about the ideal gas. What is meant by ideal gas? It is also known as a perfect gas. So the gas which obeys all the gas laws at all ranges of pressure and temperature is known as ideal gas or perfect gas. Practically no ideal gas exists, that is, no real gases are ideal gases, but they behave as a ideal gases. So because of low pressure and high temperature, molecules of gas are far away from each other, so there is no any molecular attraction between them. For example of real gases are air, oxygen, hydrogen, N2, helium, etc. So internal energy of perfect gas depends on a temperature. So the equation is PV is equal to nRT for ideal gas law. So we assume that the work medium is ideal gas and the process is as follows. So in this lecture we see two processes, isochoric and isobaric process. So first we see the now we see isochoric process, means in this process volume is constant and the process is also known as constant volume process. In the graph we seen that the graph is plotted pressure against volume, and the pressure changes from value or from state 1 to state 2, but volume remains constant for the both states. That's why the process is known as constant volume process. All heat supplied is stored in gas in the form of internal energy. So, since in this process there is no change in volume, so no work done. So, we get the constant equation for this constant volume process is P1 by T1 is equal to P2 by T2, where V1 is equal to V2. So, work done by the gas is equal to PdV, which is equal to 0. So, change in internal energy, we know that the change in internal energy equation is mcv dt. We consider m is equal to 1. So, we get the internal energy value, where Cv is a heat capacity at constant volume. So, we know that delta U is equal to, means internal energy equation, delta U is equal to Q minus W. So, the delta U is equal to Q because our work done is 0. So, W is equal to 0. Then the equation is delta U is equal to Q. So, during an isochoric process, heat enters, leaves the system and increases the internal energy. So, final equation for the internal energy is delta U is equal to Cv into delta T, and the unit of this equation is joules per second. Now, moving forward for the constant pressure process, which is also known as isobaric process. As shown on the graph, the pressure value from state 1 to 2 is same, and volume value it changes from state 1 to 2. So, the equation we get is W, means work done, is equal to PdV is equal to P into bracket V2 minus V1, means P delta V. So, the Q is equal to Cp into delta T, which is difference between temperature T2 minus T1. So, the Cp is heat capacity at constant pressure. Now, equation becomes for the internal energy is Q minus W is equal to delta U. So, the value for Q is Cp into delta T, and the value for the work done is P into delta V. So, the final equation for the internal energy is Cp into delta T minus P into delta V. So, we have to know in detail for the isobaric process. Once again, I repeat you, in isobaric process, pressure of the system remains constant. So, heating of gas in frictionless cylinder piston example arrangement is example. So, heat supplied to a gas is utilized to increase internal energy as well as to do some work. So, this process now considered m kg of gas is heated at constant pressure from state 1 to state 2. Okay, now we get the final equation is delta U is equal to Cp into delta T minus P into delta V. So, part of heat is used by this system to do work on the environment, and the rest of the heat is used to increase the internal energy. This is the whole isobaric process. The next processes are seen in the next lecture. Thank you. If you have any doubts, then your doubts written clearly in the comment sections. Thank you.